Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This presentation illustrates the use of a low-cost camera with the Arduino GIGA R1 Wi-Fi board. This tutorial provides introductory guidance on attaching a camera to the Arduino GIGA R1 Wi-Fi board. The key steps in this tutorial are: understand the prerequisites to use a camera on the GIGA board, and run some simple examples of camera applications. A previous tutorial covered the basic features of the Arduino GIGA R1 Wi-Fi board. Naturally, one must attach a camera onto the GIGA board to use the corresponding features, since the GIGA does not have an onboard integrated camera. The output from the camera is not displayed directly on any device connected to the GIGA board. Instead, the output is transmitted to a host computer through the serial port. A simple program on the host computer processes the data for visual display. Therefore, not only must one select a suitable camera, but must also pay attention to the processing of the data captured by the camera. There is a popular program called Processing that can read the data from a serial port on the desktop and display a corresponding image in a window on the desktop. Processing has been around since 2001 and was the inspiration for the original Arduino IDE version 1 series. Arducam invented the world's first high-resolution serial protocol interface, better known through its acronym SPI, camera for Arduino in 2012. Since then, Arducam SPI cameras have been filling the camera needs that were previously impossible to cover with the Arduino board's native camera support. These SPI cameras are suitable for a broad range of devices, not just Arduino boards, but can also be utilized on other devices that have the SPI and I2C connectors. Some of the camera models supported by GIGA are OV7670 and OV7675, HiMax HM01B0 and HM0360, and finally GC2145. Since SPI and I2C are the most popular interfaces on all of those microcontroller boards, Arducam uses SPI for image data acquisition and I2C, or I2C as it's commonly called, for configuring the image sensor register settings. The SPI interface is the fastest of low-speed peripherals compared to other one-wire I2C, UART, and other interfaces on the microcontroller. It is a bus-style interface with one master and several slave devices connected to the same bus with individual chip select signals. The Arducam camera's SPI speed is designed to be 4 megabits to 8 megabits per second for compatibility with both 5-volt and 3.3-volt systems on different Arduino microcontrollers or even other ARM processors, because the 5-volt to 3.3-volt level shifter timing will cause communication errors at high speed. The camera coprocessor is referred to as Arduchip, which handles complex and fast speed camera video signal timings and then sends the images to a large off-chip frame buffer. This method offloads the processing tasks from the GIGA to the coprocessor. Thus, the GIGA only needs to issue the capture command and then process the image in a byte-by-byte order at its own speed. The image itself is retained in the Arduchip frame buffer until it is flushed. Arduchip connects to the image sensor as shown in the diagram. GIGA only needs to send a capture command to read the image data in a slow byte-by-byte order. The image is retained in the frame buffer until it is explicitly flushed. Arduchip provides an interface standard to permit different cameras to interface to a single board microcomputer such as the GIGA. While the Arducam 20-pin camera connector was promoted as a standard, it has quickly been delegated to a niche segment. Initially, the support up to 5 megapixel resolution sounded very appealing to development work with cameras using the GIGA. The camera supporting the 20-pin standard can interface to the GIGA board without extraneous wiring considerations. Arducam supports the STM32 microcontroller family through its 20-pin interface. There are 17 different performances and features with this interface to STM32 boards. Indeed, for the low-end SPI camera series, Arducam is a good choice for cameras. Arducam's Arduino cameras are designed for less powerful Arduino boards and are mainly for capturing high-resolution still images or a few seconds short movie clips. It is suitable for battery-powered IoT applications that require taking a large still image and then storing it on an SD card or sending the image over Wi-Fi and uploading it to the cloud for future image processing. Battery-powered applications like CubeSatellite, that is CubeSat, you can power off the Arducam completely using a MOSFET to cut off the camera power pin to reduce the power consumption to zero. With multiple camera applications like panoramic photography, you can connect more than 4 Arducams on the same bus and take images at the same time, and then poll each camera to retrieve the image data one by one. Tiny machine learning, TinyML, with TensorFlow Lite linked explains in this tutorial. It is unsuitable for video streaming, surveillance, or recording because the SPI interface throughput is not as fast enough for MPEG video stream. Four different camera models are shown on this slide. This slide provides more detailed information on the specific pin connections from the microcontroller on the GIGA board. The use of a standard header module alleviates the challenges ensuing from using wire connectors to the respective pins. Just keeping 20 pins constantly connected without soldering is a task by itself. The OV7675 is a high-performance VGA sensor designed specifically to address the growing demand for consumer electronics from emerging markets. Its small optical format enables ultra-thin camera modules which, combined with its excellent low light performance, make it a very attractive solution for the Arduino GIGA board. It supports the full functionality of a single-chip VGA camera in a small footprint package. It provides full-frame, subsampled, windowed images in several formats with user control over image quality, formatting, and output data transfer. All required image processing functions, including exposure control, gamma, white balance, color saturation, hue control, defective pixel cancelling, noise cancelling, are programmable through user settings. The image size format from the camera can be set through the Arduino sketch. The three resolution sizes supported by the camera are listed in the table. There are a variety of output formats supported by the Arduchip interface. For the purposes of our simple demonstration, we will stay with the RGB 565 format that is very common at the lower end of the specifications because it reduces latency in data transfer as opposed to 24-bit color where 1 byte is used for each primary color. This latter format is known as RGB 888. The OV7675 supports both automatic and manual exposure control modes. Both automatic exposure control and automatic gain control functions are interactive. The OV7675 supports automatic white balance function to adjust red, green, and blue gain to make a white target be white regardless of lighting. The low voltage color CMOS image sensor supports the full functionality of a single chip VGA camera with best in class low light sensitivity, significantly reduced noise, and outstanding color reproduction. The camera provides full frame, subsampled Windows images in VGA and lower resolution formats. The image array can operate up to 30 frames per second in VGA resolution with user control over image quality, formatting, and output data transfer. It is an economic entry-level solution for camera applications. The limitations of the OV7675 camera with respect to streaming rate and internal memory preclude it from being used in applications for video streaming or surveillance. On the GIGA, this OV7675 is limited to 2 megabytes internal memory if the GIGA's memory is allocated to only one core, and 30 frames per second at VGA resolution which itself is the upper limit for the camera. The demonstration uses a desktop computer connected to the GIGA board, which has the camera mounted on the dedicated 20-pin connector, an external flash memory, that is the SD card, at the USB-A port. This memory is necessary for VGA output at 30 frames per second. It is not necessary for lower resolution output. The GIGA board is connected to the desktop computer through the USB-C port. There are two basic phases in the demonstration. First, the image acquired by the camera attached to the GIGA board is transmitted to the serial port after being written and read to from the SD card attached to the GIGA board at the USB-A port. Second, the data at the serial port is read by a simple program on the desktop computer to display the corresponding image. The flash memory of the GIGA board is limited to 2 megabytes. Even after full allocation of the memory to the core running the sketch, in this demo the M7 core is used, there is space only for the image at QVGA and QQVGA resolutions. When the camera is set to capture at VGA resolution, then the SD card storage feature must be used. In this demonstration, the sample program camera-raw-bytes.ino provided by Arduino is used to capture the image from the camera. All three available resolutions for the camera were tested successfully. For VGA resolution, the SD card acts as the image buffer. Owing to this variation, the image display by the processing program on the desktop becomes slightly more laggy than desirable. So while acquisition of still images is not an issue, streaming video from the camera is impractical for streaming purposes. Processing is a flexible software sketchbook and a language for learning how to code. Since 2001, processing has promoted software literacy within the visual arts and visual literacy within technology. It is very practical in displaying the camera data transmitted to the host computer by the GIGA board. Processing is an open source and is available for Windows, Mac OS, and Linux. Projects created with processing are portable. The projects can be used on Windows, Mac OS, Android, Raspberry Pi, and many other Linux platforms. This demonstration uses the standard example provided by Arduino to process serial data from a camera on the GIGA board. Some key settings for the camera and the desired image acquisition mode are camera resolution as expressed in width and height in pixels. Camera image is in color and therefore the variable use grayscale is set to false. Since the processing app will read data from a serial port, it needs to know which serial port and at what speed, which is expressed as baud rate. It should be noted that the specification for the serial port varies with the operating system conventions of the desktop computer. When the Arduino sketch is uploaded to the GIGA board successfully, the sketch will run continuously without interruption, collecting images from the sensor and forwarding the contents of the frame buffer to the serial port for use by the processing app on the desktop computer. Do not open the traditional serial monitor window for the sketch. If it is open, then close it immediately to release the port for use in the following step. Launch the processing app on the desktop to display the data received at the serial port. The display image refreshes continuously as new data is read at the serial port while the app is running. Let's go ahead and do the second demonstration at VGA resolution. We will use the same original default Arduino sketch, camera capture raw bytes, for this demonstration. For this demonstration, we will use an image size of 640 by 480 at 8 bits per pixel, which represents the standard VGA standard. So there are a few changes that we need in the parameters. The first one is to indicate that we're using VGA with this definition, and we will keep the output format in RGB as shown there. There are some examples and references for your use later on. So let's start with first the obvious one, which is the camera header has to be there. But we've added another include file for the SD-RAM. Since at 640 by 480 at 8 bits per pixel, we will need approximately 2.4 megabytes of memory, and the GIGA has only 2 megabytes. We have to rely on auxiliary storage, SD-RAM. So let's define the header for that. And then scrolling down, we will keep the camera definitions as before. So we include the header file, instantiate the camera, enable the cam object entity, and ensure that the image mode is represented as RGB. Now, please take a look here. Previously, we were using a frame buffer in memory. since we're using the SD card for the frame buffer, we need to simply tell the program that the definition for the start of the frame buffer is the start of the SDRAM address. Once that's done, then the rest of the code is almost the same except for the resolution, which is defined in here. Obviously, using the SDRAM makes the image refresh a little slow. You're writing to SDRAM and then you're reading from SDRAM, so processing will be a little slow and laggy. But let's go down to the rest of the code, and you can see there's very little change in here. So we can go ahead and compile this code by clicking on compile. The code compiles successfully, naturally, because we haven't made any significant changes. And let's go ahead and upload to the board. So it's going to go through compile again, and I just want to keep these two steps separate as a habit. So once again, we get confirmation that the compilation succeeds, and now the code is completed uploading to the board. So we need to go ahead and launch. The image captured by the camera is displayed continuously in a window, as shown in this demonstration. As you can see, the image is updated in a very laggy way, owing to the fact that the data has to be written to the SD card and then read from the SD card. And as I zoom in closer, you can see the window is still demonstrating what it sees clearly based on ambient lighting conditions. So I hope that this serves some useful purpose in demonstrating the fact that the GIGA 1 can run the OV7675 camera at 640 by 480 resolution. This tutorial was a very simple introduction to using a camera on the Arduino GIGA R1 Wi-Fi board. The prerequisites for using the camera were enumerated. The camera was installed on the GIGA board through the dedicated 20-pin connector. The app called Processing to process the image data from the GIGA board to the desktop was installed. Some key image settings for the camera were changed in the sample sketch. The sketch was uploaded to the GIGA board to run indefinitely. The processing app was run on the desktop to display the image received at the serial port from the GIGA board. That's all, folks. Please provide feedback in any which way you can. This presentation was prepared with assistance as noted on the slide. My apologies if I have unintentionally or inadvertently omitted anyone or any resource. A very big thank you to y'all Come back to the channel soon.